Today we're going to continue discussing measures of center and variation, but with respect to what it means to be skewed and what it means to be quote unquote normal, right? So symmetric. So when we talk about things that are symmetric, we're talking about specifically a normal distribution, right? So that bell curve. Something that looks like this, where my mean, my median, my mode, all right in the middle at the peak, right? And so I kind of draw up and I hit a max and then I head down and I have my bell curve. This is what we want to happen when we gather data, that we want it to be normally distributed. And you can imagine in the real world, you're probably not getting your mode, your median, your mean to be all in the same spot at the same time. But there are tests that we can run that we're not going to run in this class, but if you were out actually gathering data, that you can test the data to see, are you indeed close enough to this bell curve for me to call you allegedly normal? If not, then you're skewed, and then we got to deal with you in a little bit of a different way. You could be skewed to the left, and if you skewed left, oh, he didn't want to come on. If you're skewed left, that means I have an outlier down here to the left that's dragging this mean down. So my mode and most of my data is up here on the right, but I have some guy that's dragging him all the way down to the left. And so if I'm skewed to the left or negatively skewed, it's because my tail is shooting off to the left. So you want to look for the tail. If your tail is shooting off to the left, then it's a negative skew because you have this low number dragging your mean down. Probably not your median, but definitely your mean. If you're skewed to the right, then this is our Bill Gates situation, right? Most of our people were over here in this normal range of salaries, and then here's Bill, right, with all of his money hanging out all the way down out on the right, and so he dragged this mean up. And so the tail is shooting out this way. And so if I have an outlier to the right, my tail shoots to the right, and he's positively skewed. We're only concerned about stuff in this course that's normally distributed. And you'd be surprised how many things actually turn out to be normally distributed after you're done collecting the data. And if something is normally distributed, or at least really close to being normally distributed, we can use something called a range rule of thumb, which I will not call it that because it sounds a lot like range rule that we had, that max minus min divided by 4. This is really more based upon the distributions that we're going to look at in a few slides. The idea of this is that for the majority of data sets, 95% of the sample values will lie within 2 standard deviations of the mean. And so if you watch the video of Arthur Benjamin of Why Statistics, and he says, I want everybody to leave high school and college knowing what it means to be 2 standard deviations from the mean, and he means it, it's because of this. Most values that we consider usual or unusual follow that pattern. So your usual minimum value is that mean, and then you subtract out 2 standard deviations. And the max usual value is the mean plus 2 standard deviations, and that is the range of usual values, right? So if you want something that you say, well, most of the time, right, we say stuff like that. You say, oh, well, I want it to be 10, but it's not usually 10. Sometimes it's 9, sometimes it's 11, and that's okay. It's okay because it probably fits this usual value rule. You can estimate that range, that standard deviation if you don't have it, but we have calculators and we can plug in values and it will give us S and it will give us X bar, and all we have to do is start multiplying and adding and subtracting. And if you haven't watched the How to Use 1-vars, you're certainly going to want to do that because it will show you how to get these values without having to crunch them by hand. Measures of variation, the closer they are together, the data sets, the smaller the standard deviation. And if all of your numbers are the exact same, so you have like 3, 3, 3, 3, 3, 3, they're all the same, so they don't vary, so your standard deviation is 0. Well, that doesn't happen a whole lot, as you can imagine. What does happen a whole lot is that it's normally distributed. And if it's normally distributed, we can use our most favorite rule for distributions, the empirical rule. You can thank Gauss for this. I'm a little lazy, and I usually say 68, 95, 99. It is technically the 99.7. Sometimes you'll see people use 99.9. I'm not too worried about this mess out here. This is what Gauss was going for. If you have something that's normally distributed, about 68% of all the data values will fall within one standard deviation from the mean. So you put your mean on the wall with your sticky note, and you say, all right, I'm going to measure my standard deviation out, that distance, once to the left and once to the right. About 68% of the values in my set are going to be in that shaded zone. About 95 for 2 standard deviations. This is what creates our minimum usual value and our maximum usual value, right? So that range of usual values. And we kind of let it go 3 standard deviations. And sometimes when we're talking about outliers, we'll use a point within that 2 to 3 steps to be our cutoff. And that's about 99.7%. So 1 standard deviation up and 1 standard deviation down from my middle, we'll have 68%, about 34 on each side, right? Because we're talking about something that's symmetric. 2 standard deviations, up and down, that's going to cover the 95%. So this is my min usual value, and this is my max usual value. 3 standard deviations would be 99.7, and then after that, we don't worry about it too much in this little zone right here. If you're more than 3 standard deviations up or down, you're pretty unusual. 0.1% of whatever that population is. This is a very hard and fast rule. Gauss said, I'm not interested in compromising. It's 68, 95, 99.9, and we're going to go with Gauss's hard and fast rule for distributions when we do our work this semester. But, of course, outside the textbook, it's probably not that cut and dry. So Chebyshev comes along and says, Gauss, bring it down a notch. Maybe it's not exactly 68, 95, 99.7. Maybe it's at least, though, this percentage, where K is the number of standard deviations the way we're talking about. So Gauss said, listen, maybe Chebyshev said, maybe it's not 95 for 2 up, 2 down. Maybe for 2 up, 2 down, it's at least 75%. So it may not be 95%. It might be 88%. It might be 60, well, not 67, but maybe like 77%. At least 75% of your data will be within 2 standard deviations of the mean, and at least 89% for 3 standard deviations. So maybe not exactly 99.7, but certainly at least 89. So if you're normally distributed and you're not Gauss's perfect world, but you're still considered normally distributed, Chebyshev says it will be at least the 75 and the 89. We don't worry about the 1 standard deviation up and down because certainly there's going to be something in there. That would be a 0, right? 1 squared over 1 minus 1. Well, of course there's going to be something in there because you're close to the mean. So we'll talk about Chebyshev a little bit in Chapter 3, but after Chapter 3, we will only be talking about the empirical rule. That will be the rule that you want to have memorized. That's also what we're going to use as a basis of comparing sets of data, like using the coefficient of variation. And so there's an example at the end of 3.3 in your homework that talks about lines in banks. So there's something to be said for being predictable. So if you go to a restaurant and you always have good service, right? They're always on their game, but maybe they're a little slow. So every time you're in there, you know you're going to be there for a while. I'm thinking like melting pot here, right? You go to the melting pot, you're there for like 3 hours. I've only been there once. It was good, so I guess I could say 100% of the time it's been good. But, you know, it takes a long time, but you know it's going to be good, so you don't mind the wait. Let's say that there's another restaurant that is also pretty good, but sometimes you're there for an hour waiting for something to drink, and sometimes they're on their ball right away. How do you compare the rates of their service? Because one is a big chain, and maybe the other isn't. Maybe the other one is just some small little place in Davidson, and you can't beat them up too much because maybe they don't have the staff and the manpower that Melting Pot has. You use the coefficient of variation. You would take the standard deviation from that sample and you would divide that number by the mean and you would change it over to a percent, and that's called your coefficient of variation. You would do the same thing if you're talking about a population. So let's say I go to the Melting Pot and I write down all the time that I had to wait to get a glass of water, and I find that sample standard deviation, and it's let's say an 8, and the mean is, let's say, a 20, and I can change that to a percent using my handy calculator. 8 divided by 20 is 0.4. Change it to a percent, and that would be a 40%. That means that their variability, their unknowing of what is going to be happening at their restaurant is about 40%. So 40%, maybe not so bad. You would say, well, that's pretty predictable. So let's say you go to the other restaurant and their mean is also a 20, but let's say their sample standard deviation is a 13. Well, actually, yeah, let's go ahead and say that. Well, now they're 65%, so they're much less predictable. So the higher the CV, the less predictable that you are. And depending on what that predictability represents, right, maybe something more important than how long it takes you to get your water at a restaurant, that may be something that is very important to consider. And so coefficient of variation is something that we can use to compare two things that are similar but not the same. And we're going to base that variation upon the 68, 99, 95 rule. So we talked about a lot of things, and 3.2 and 3.3, range, standard deviation, variance of range rule, empirical rule, Chebyshev's rule. We talked about mean, median, mode, mid-range, lots of definitions, and lots of numbers and formulas. And so you may want to pull out that formula card and have that handy and maybe make some notes from your 1VARS video on how to find all of those very important numbers.